Advancing what we know about related rates is we're going to look at some problems involving areas and volumes here. So grouping them together, radius of a circle increasing at a rate of 3 inches per second. Let's translate. Radius of a circle, let's use r. So increasing at 3 inches per second, I would say dr dt is 3 inches per second. Find the rate of change of the area of the circle, dA dt, when the radius is 3 feet. So what we've got here for given information, my radius is 3 feet, and we'll start looking. Oh, I've got a little concern there because we've got 3 inches per second and we've got 3 feet. So let's change this. Let's call it 36 inches as far as what my radius is. Now remember, if you picture a circle that's being, I can't say inflated by air because that would be 3 dimensions, but really what we've got is this circle is just growing. If the circle is growing, what's changing? Well, the area is, the radius is, the circumference is, all that, the diameter is. So that radius is 3 feet. That radius is 3 feet is what it looks like when we snap the picture of this thing that's moving. It's not always 3 feet because that would make it a constant. So I need an equation to relate these variables so I can take the derivative with respect to time and then plug in my information. So how about an equation to relate variables? How about area of a circle is pi times the radius squared. So if I take the derivative with respect to time, dA dt would be 2 pi r to the first times dr over dt. Again, remember every variable is a function of time. Hey, isn't it interesting? dA dt would be the rate of change of the area of the circle. And here's 2 pi r. 2 pi r, isn't that the formula for circumference of a circle? So the rate of change of the area of a circle would be related to the circumference of a circle. Interesting. Anyway, so now we just take our stuff and we start plugging it in. So my dr dt is 3 inches per second. My radius is my 36 inches. I guess I should probably start including some labels. Inches per second. Let's make this halfway clear. So my 3 inches per second, and then I've got this 2 pi. So under these conditions, what have we found? 2 pi times 3, so 6 pi times 36. How about 216 pi square inches per second? Well, let's think for a second. Square inches, what changes in square inches? Area does, and this is supposed to be the dA dt, the rate of change of the area of that circle. So we multiply it out. Nope. Tell you what to watch out for. Don't forget your pi. For whatever reason, we tend to do that. Second one, now we're talking about volume. Gravel is falling onto a conical pile at a rate of 10 cubic feet per minute. Well, let's see. What changes in cubic feet per minute? I think that's volume. So gravel is falling at a rate of 10 cubic feet per minute. That is, we're going to call that dV over dt. So what's that? dV over dt is 10 cubic feet per minute. And use the units to help you understand what it is. Well, it's cubic, so it must be volume, so let's call it V. The diameter of the pile is 5 times the altitude. Well, let's picture this for a second. I'm in a gravel pit, and I'm watching stuff fall off the conveyor onto a pile. Well, it's going to make a cone, a conical pile. What's changing? Well, the height of that pile is changing. The circular base, we're assuming the base is a circle. The circular base is going to be getting a little bit larger, so that would mean the radius of the base is, that would mean the surface area of this thing is. We got all kinds of stuff changing. The diameter of the pile is 5 times the altitude. Let's translate that. Diameter of the pile is 5 times the altitude. So altitude, I'm going to call it height. D for diameter is equal sign 5 times the altitude. We'll call it h. Find the rate of change of the height of the pile. The rate of change of the height of the pile. How about dH over dt when the pile is 10 feet high? Is the pile always 10 feet high? No. We said that's a variable. If it was always 10 feet high, we'd call it a constant, so it's not constant. So we know that the pile is 10 feet high when we take our picture of the situation that's going on. So I need to relate all this together. Well, what's my relationship between V and H? That's the ultimate thing I want to relate. How about volume of a cone? Volume of a cone 1/3 pi r squared h. Mr. Perkins, I'm never going to remember that. Well, isn't a cylinder, going to find the volume of a cylinder, isn't that a stack of pancakes? So you'd need to know what the area was of one pancake and know how tall the stack was. Well, there's your pi r squared times your height. And then a cone isn't all of the cylinder, it's just a fraction of it. What fraction is it? It's 1/3. So 1/3 pi r squared height h. Here's the tricky thing. We have three variables in that equation I just wrote. We have v, we have r, we have h. They're all changing with respect to time. They're all changing in our picture, but we know nothing about r. So we want to relate v with h. So our goal would be to get all the r's out of the equation. So we need to represent r's using some of these other variables in the problem. Let's come over here and say, hey, you know what? A d is the same thing. A diameter is the same as 2 r's. So if that's the case, then my radius is the same thing as 5/2 times an h, or 2.5 h's. So if I want to get the r's out of the equation, let's represent them using h's. So this thing is really the same thing as 1/3 pi times 5/2 h being squared. And now you can make an equation. So make an equation that has all h's in it. So 5 squared is 25. 2 squared is 4, so 25 over 12 pi h cubed. So now you got an equation that has all h's in it. We go to take our derivative, so now our derivative, our dv dt that we were given. So 3 times 25 over 12 would be 25 over 4 pi h squared, and remember h is a function of time, so a little chain rule, dh dt. Now it's our substitution. We're done with the calculus, now it's substitution. Start plugging stuff in. We were given that the dv dt is 10 cubic feet per minute. We've got a 25 over 4 pi. H were we given? H was given to be 10 feet high. And dh dt is what we're trying to figure out. So it looks like we're going to be dividing by 100 square feet. And we're going to be multiplying by 4 over 25 and then dividing by pi. So how about dh dt? Make sure I don't mess this up. We've got a 10 on the top, 10 cubic feet per minute. We're going to have a 4. And we're going to have on the top with it. And then we're on the bottom, we're going to have a 25, a pi, and a 100 square feet. So as we're trying to figure out what our units are, let's see. Looks like square feet will cancel with cubic feet, and we'll end up with feet per minute, which makes sense because height would be changing in one dimension with length. Do a little canceling. 10 and 100 would cancel to be a 1 and a 10. 4 and 10 would be a 2 and a 5. So how about 2 over 25 times 5 would be 200, 125, 25 times 5, over 125 and pi feet per minute. So interesting. That's pretty small. We can make a decimal out of it. You see what we come up with. There's nothing wrong with doing that. Just make sure your answer is accurate to 3 decimal places. And one other thing, make sure if you're going to use the slash, like I know a lot of students like to do, that answer I just wrote is not the same as the answer in the box. If you're going to put it, make it the same as the answer in the box, you need a quantity around your 125 pi, because order of operations says I would divide 2 by 125 before multiplying it by pi. So make sure you put a quantity around it so we know we multiply first. Anyway, that's areas and volumes and related rates.